Okay, let's start. So first, let's recall the definition of Horus numbers, and let's discuss in a bit more detail the relation between the combinatorial approach and the geometric one. So for simple Horus numbers, let's recall our combinatorial definition. We said that H, we wrote G here, Hg mu, where mu is mu1, mu2, and so on, mu(n). It's the following thing. First, we write m as 2g minus 2 plus n plus size mu. So this is size mu is the sum over OI from 1 to n mu I. Okay. If you recall our discussion of the Riemann-Horus formula, this m, it corresponded to in the geometric picture, it corresponded to the number of simple range points.
Sorry, Petya, I want to interrupt you. In fact, finally you are writing in IDRO, and so we didn't. So the IDRO aren't recording now. In fact.
Sorry. Yes.
That's what I realized just now.
I forgot to. Yes.
Yeah.
I need to enable the.
So, like, you need to share the screen?
Yes, just a moment. So how do I go back?
I hope that you in the classroom will still have a good transparency of the IDRO, but yeah, I'm sorry. Yes. So now at least something we see.
So now it's fine?
Yeah, now it's fine.
Mm-hmm. Thanks.
But you see your transparency, I mean, in the classroom is okay, or?
Всем хорошо видно? Не отсвечивает, может, повернусь как-то? Нормально?
Because I mean, we are online, could just see on IDRO and. Yes.
All right, so
yeah.
Let me repeat this. We are now going to recall the definition of simple Horus numbers, Hg mu, where mu is this collection of mu1, mu2, and so on, mu(n), where the size of mu, so size of mu is the sum over all mu I, and we define this m to be the following expression. It has, so this formula has a geometric meaning, which we'll recall in a moment. But first, let's start with combinatorial definition. So we say that H G mu is the so actually, let me at this point let me mention that there are several different definitions of what we call Horus number, and in the literature you can encounter various definitions, and sometimes so you need to actually, if you see this Hg mu, you need to actually look up the precise definition which is given in the particular paper, because these definitions, they differ by certain combinatorial factors. So the numbers will be different if you use different definitions. The meaning is essentially the same. They differ by simple combinatorial factors. But this difference happens. So between different definitions. And in fact, let me actually give two definitions which will differ by a combinatorial factor. And then we'll see what is this difference and how it is related to what we did on the seminars. So the more common definition is just this. It's just the number of, so just 1 over n factorial times the number of collections of m transpositions sorry. Number of collections of m transpositions such that their product has cyclic type mu, and they act transitively. All right, so this is one way to define the Horus number. Just, again, what we're used to, just taking the number of all possible collections of m, ordered collections of m transpositions, such that the product has cyclic type mu, and as a whole, they act transitively on our numbers from 1 to 7. All right, but actually, which we will finally see today in the seminar, if we want to compare this with what is recovered by topological recursion, so then you need to actually if you use this definition, you need to actually multiply it by the number of automorphisms of mu. So if you use this definition, so you need to actually say, here is the number of these collections, and then you need to multiply it by the number of automorphisms of mu. What are automorphisms of mu? So for instance, let me give you an example. If n is equal to 1, then what is the number of automorphisms? If n is equal to 1. No. Automorphisms of mu as a collection of n numbers. So in how many ways can you reshuffle your n numbers such that the order remains the same? So if you have just one number, what is the number of automorphisms?
So Peter meant that mu is equal to the tuple mu1, etc., mu n, such that mu1 plus etc. plus my mu n is equal to modulo mu.
No, but I mean, we fix a mu. If you have some
Yeah. But
mu is equal to mu1, and so on, mu n. So if n is equal to 1, then the number of automorphisms is always 1. Then this doesn't affect. This factor doesn't affect anything at all.
How do we define an automorphism?
Well, I will.
Because my idea was if we have n equal to 1, then we have one n cycle, and it has n automorphisms. It can be conjugated by n.
No. We consider automorphisms of mu as a collection of n numbers. So you have an n tuple of numbers,
Right, yeah.
and you can consider automorphisms of these things.
So the number of automorphisms will be like product of parallels corresponding to sizes of mu I.
What do you mean by sizes? Numbers of identical elements. Let's see let's consider more examples. So maybe we will see it in a moment. So let me move this downstairs and let's discuss this in a bit more detail. So suppose you have now some example. So you have 1, so mu is equal to 1, 1, 3, 3, 2, 1. Okay? What is the number of automorphisms? What is the number of automorphisms?
6 times 2.
Yes?
so yeah, in the end, finally, it's just a product of numbers of factorials of coincides parts, number of coincides, factorials of number of coincides parts in the tuple 1, 1, 3, 3, 2, 1.
What is the definition? Let me now tell the precise definition. So suppose you have an ordered list of numbers, mu1 and so on mu n. Then you have, suppose you have a bijection on this, on these m, on those m positions. Suppose you have a bijection between these m positions. And the number of automorphisms is the number of such bijections for which the ordered list remains the same after applying these bijections. Okay? So for instance, you can, if you interchange 1 and 3, it's not an automorphism. But if you interchange 1 and 1, it's a non-trivial bijection, okay, of this list of n elements, of ordered list of n elements. But the list remains the same, so it's an automorphism. Okay? So is the definition clear? Is it clear? And of course, like Guardo said, we can compute the number of automorphisms just by counting how many duplicates you have. So you have this 3 here appears 2 times, 2 appears once, and 1 appears 3 times. So you need to multiply factorials of the counts of all the numbers. Yes? Is it clear? How do we get 12 in these cases? Okay, but you can also, so this is one way you can just manually plug this, or you can define it like we have in the homework for monotone numbers, but the same actually works for simple Fourier numbers. So you can say that in this case, let's count not just the ordered collections of transpositions, but these collections with additional structure. Namely, this is equal. Okay, let me move this So this is actually equal to 1 over n factorial times the number of transpositions, collection of transpositions, again, same thing. But also, we count, we look at the product, so, and with numbered cycles, in the cyclic decomposition of the product. And with the same conditions. But so the conditions are the same, only you require that, in this case, you require that here we said that the product has cyclic type mu, and here we say that I cycle has length mu I. And then the same thing. So is it clear why it is the same, actually? So let's look at this thing here. So we look at some disordered collection of transpositions. Okay, so let's think about what we have here. So we count all possible collections of M transpositions with additional structure. Okay, so we take our M transpositions. We look at the product. It has some cyclic type, and we introduce some ordering. So we consider some ordering on the cycles. Okay. I mean, if you have the cyclic decomposition, canonically it's not ordered, right? There is no natural order on the cycles in the cyclic decomposition of a permutation. But we introduce some order. So it has, there are how many ways to do this? Introduce some order on the collection of cycles in the cyclic decomposition. Not n factorial, but some k factorial where k is the number of cycles, right? We introduce order on the cycles, on the list of cycles, on the set of cycles. So the number of ways to do this is k factorial, where k is the number of, sorry, it will be actually, sorry, yes, this will be actually equal to n, yes. This k is actually, you said it correctly. Okay, sorry, this is n, okay. Because we want the cyclic type to coincide with mu, and length of mu is n, yes. So it's n factorial, in fact. Ways to do this, but suppose that all cycles had different lengths. Okay? Suppose that all your cycles, there are no two cycles of the same length. Okay? Then, will this actually, so in this case, this means that all mu's, mu1 and so on, mu_n, there are no duplicates there. Okay? Will then this definition differ from that one? No, it will not, because out of all possible orderings of the cycles, only one single ordering will be such that the I cycle has length precisely mu I. On mu I, you have some order there. mu I was an ordered collection of numbers. Mu was an ordered collection of numbers, okay? So then if all the mu i's are different between themselves, then there is, and in general, the cyclic type corresponds to this mu, there is one single way to order the cycle such that the length of the i's cycle is the same as mu I, okay? Yes? So then in the case where all mu i's are different, then automorphisms, how many automorphisms do we have with all mu i's? One, and this definition is precisely the same as we have here. So this is the same. If all mu i's are different. Is it clear to everyone? And now if you have, suppose you have two coinciding mu i's, let's say mu1 and mu2 coincide, and all the rest are different between pairwise and between themselves, and there's two mu1 and mu2. What then? Then in the first definition, this guy will be equal to 2, right? Number of automorphisms, because you can interchange 1 and 2. And the order at least mu1 and so mu(n) remain the same. Okay? And in this definition, you have two ways to order your cycles such that this will be, with this condition, will be satisfied. Right? So now is it clear? And as we will see today during the seminar, when we will finally complete our problem from 2 weeks ago, where we compared omega 0.3 computed by topological recursion with what we get just by counting Fourier numbers, we will see that in fact you need to use these definitions in order for them to coincide. And the same happens, the same is true for monotone Fourier numbers which you have in the homework. You need to use this definition. The only difference is that in the case of simple Fourier numbers, in the derivative function, we wrote 1 over m factorial. Now, let me mention this briefly because we are already talking about this. So for simple Fourier numbers, the derivative function h g n is sum over mu1 and so on mu(n) from 1 to infinity. 1 over m factorial. M factorial is important here. 1 over m factorial times h g mu1 and so on mu(n).
We're usually writing just mu instead of mu1, mu(n). Let's maybe write mu because of to not mess with like more general Gauss numbers. Yeah.
So this is the generating function for simple Fourier numbers, which we compare them with what we get by topological.
Yeah. Peter here wrote G as a upper script, but it's just the same. Just maybe it's more convenient to write it in this way. It means just the same. This upscript as a subscript as before.
We talked about this, I think, either last week or 2 weeks before that. We want to, because for Fourier numbers, sometimes you have this definition not in terms of G, but in terms of M, the number of transpositions, and then you write it as M mu, and in order not to confuse G and M, we decided to, for Fourier numbers, to always write G in brackets as a superscript.
Мы иногда реал в определении самого числа складываем, а иногда только когда складываем числа в ряд. Причем принципиально разных способов, почему мы не делаем все время одним способом, чтобы не путаться.
Мы на самом деле вот один m-факториал всегда только в производящий ряд включаем.
Еще про домашку, там написано, что один m-факториал.
Домашки, да, давайте я здесь прокомментирую. Actually, I wanted to say this right now. So, like I said, why I started to write this generating function, because for monotone Lewis numbers, you do not need this 1 over factorial. You do not want it. For monotone Lewis numbers, the generating function which we consider, you need to take it without 1 over m factorial. Why does this happen? Because you see here, in fact, if we have these transpositions, then their order is not really important. I mean, of course, if you change the ordering, you get a different answer in the product, but there is a bijection between, if you have like some way to reshuffle them, some fixed way of reshuffling m guys here, then you have a respective bijection on Sn, on the results, which you get by taking the product of all those guys. And well, this means that you have actually m factorial times something there, in a way. But for monotone Lewis numbers, you have a strict ordering on tau 1, tau n. If you remember from the definition, you in the monotone case, your BIs should be strictly ordered, right? Or not strictly. Not strictly. They should be ordered, so you cannot reshuffle. They are ordered, BIs. And that's why for monotone numbers, we do not write this 1 over m factorial. So this 1 over m factorial, it corresponds to reshuffling transpositions here. And in the monotone case, you cannot reshuffle them because you will lose the ordering on the i's.
But we can if we have two same PIs.
Yes, but this is, you're right, but this is built in the definition of the monotone numbers. So we just have to remember that for ordering Lewis numbers, we consider this, or I mean, actually, if you like, we can even move this here in the definition of the numbers themselves in order to have the generating functions to be always of the same sort, but I mean, conventionally, it's written like this. But if you like, we can move it here. It's not a big deal. We want, in the end, we want to understand how is this related to what topological recursion produces, and what is the definition. I mean, like I said, there are multiple ways of defining Lewis numbers, so even if we just take this and move it here, it's okay. You get different numbers, but you understand what are they, and what is the relation to all other definitions, right? So maybe let's, actually, maybe let's do this. Let's move 1 over m factorial over there because
no. Because of in the future, it will be maybe useful to write it in this way.
No, but I think if you look up our paper, for instance, on the EP tau functions, we do not have 1 over m factorial there in the general
I suppose we have, but
no, we do not.
In this endpoint function, yeah, we do not have, yeah.
So in that sense, maybe it's even better to move it there.
Maybe, yeah. In fact, it doesn't matter, yeah.
Yeah, like I said, it doesn't really matter. You need to just, it's different ways to formulate this definition, and in the literature you can encounter all possible ways to do this, but if you look at the definition itself, it becomes clear.
Да, давайте, может быть, я повторю еще раз по-русски, да, что что мы обсуждаем последние полчаса, что действительно мы немножко вас обманули сначала, и в смысле, что надо дать довольно конкретное определение чисел Гурвица, чтобы они совпали с той топологической рекурсией, которую мы считаем. И в итоге вот эта поправка на автоморфизмы, да, получается, что вообще-то мы считаем другие числа. Это другая задача. Мы считаем другой, если хотите, комбинаторный объект. И числа получаются другие. Но мы тоже их называем числами Гурвица. Они отличаются от того определения, которое мы дали там на первой лекции на некоторый множитель. Но вот надо быть внимательным к этим там, факториальным множителям, когда вы делаете конкретное вычисление, потому что иначе что-то может не сойтись. И когда про что-то говорят, что вот какие-то... Мы говорим, что вот будем говорить, что что-то удовлетворяет топологической рекурсии, ну вот когда дело доходит до проверки этого, то надо четко понимать, какой именно объект вы считаете.
Давайте действительно перенесем один мем факториал в определение числа, чтобы у нас всегда была одна и та же производящая функция. И будем это иметь в виду. Сейчас, секунду. Вот возьмем и перенесем просто это сюда. Упс.
Да, потому что, как вы, наверное, догадываетесь, по домашнему заданию вообще разных видов чисел Гурвица их великое множество. И они все удовлетворяют топологической рекурсии, но, в общем, это другая история, но надо быть внимательным к определению.
Все одинарные либо двойные. Начиная с тройных, там уже проблемы с топологической рекурсией.
Ну.
Okay, let's for simplicity, let's just fix that for simple force numbers we include this one over factorial in the definition of the numbers themselves, and for the derivative function we will always have one of the same definition. So this will be our, from now on, this will be our convention. So is it clear? You had some question?
Здесь сумма μ, она как бы здесь мюшки неупорядоченные, да?
Упорядоченные.
Порядочные?
Да. Ну вот сумма по отдельно, по μ1, μ2, μ1, ну в смысле...
Ну, понятно, что нет условий, что μ1 меньше, чем μ2.
Нет условий, по всем, да. Сумма по всем. We sum over all ordered collection of μ's. Ordered collection of μ's.
Да, то есть если как в примере, который сейчас написан с μ на доске, сейчас его всем видно или только тем, ну, в общем, когда там 1, 1, 3, 3, 2, 1, допустим, μ, то суммируется по всем наборам вот таким вот.
So you can have like 1, 1, 3, 3, 2, 1, so it's not, you do not require they to be in like ascending or descending order, okay? So we sum over all of them. But in fact, you can see that from the definition, it's clear that if you is this guy symmetric? Are forest numbers given by our definition, are they symmetric? So what happens if you, instead of this μ, for instance, if you write 1, 3, 1, 3, 2, 1. So for instance, what happens if you write like that? 1, 3, 1, 3, 2, 1. What is the respective forest number? How is it related to the forest number for this one? With the same d?
They're equal.
They're equal, why?
They're the same forest number.
I mean, they're equal. I mean, in our definition, they're not the same because μ is ordered. So, like we consider this not as some unordered set, right? We consider this as an ordered collection. So those two collections are different. But the forest numbers corresponding to those lists of μi's, they're the same as was correctly pointed out. But why? How do we see this from the definition? From this definition, for instance. How do we see it? Yes, so you here, if you recall, we considered ordered collections of transpositions with additional structure, this numbering of the cycles, right? But if you reshuffle your MUIs, then you can just reshuffle the numberings of cycles in exactly the same way, and they will coincide then. And if they didn't coincide, then they will not coincide. I mean, am I making sense to everyone? Is it clear why, by this definition, your number remains the same if you reshuffle MUIs? Is it clear to everyone? I mean, in this definition, it's automatically clear, right? Because we said that here the product has cyclic type, but cyclic type is an unordered list of length of cycles, right? So it doesn't matter what was the ordering on MUIs, automatically here, right? And in the definition of automorphisms, we'll also see that it doesn't matter what is the order. And here as well, we can clearly see that they're the same. So this means that our H, G, mu, they are symmetric upon interchanging MUIs, right? And what does this mean for the geometric function? It's symmetric. I mean, it would have been automatically symmetric anyway. No, I mean, yes, it's symmetric upon replacing
x variables.
Xi and xj. Okay? It's a symmetric function in n variables, x1 and so on, xn. Okay? It's clear from this definition. So let's.
Да, давайте еще раз, может быть, я...
Once again, what happens if we go from ordinary simple Fourier numbers to monotone Fourier numbers? What is changed here in this definition? You remove 1 over n factorial, and you require that the toi's are in ascending order. Okay? Do you remember this from the homework? I mean, you can look it up, the definition given in the file with homework problems. So then there you can see that the definition is precisely like this, just without the n factorial. And for all the toes, they are ordered. And in fact, what you said, that there is this difference. I mean, that removing 1 over n factorial does not directly correspond to having this non-strict ordering on tau I, right? So you said this, that there is, you can actually interchange two with the same b, right? But if that's the point, you're right, they do not correspond, and that is the difference between simple Fourier numbers and monotone Fourier numbers. They are different numbers. And this is precisely because what you said, so that you can interchange, that the ordering there is not strict. That on the BIs, if the ordering was strict, then you could precisely cancel out this 1 over n factorial just by requiring that these guys are ordered. Then you would get the same numbers, right? And they are not the same.
So now, which number is bigger? Order?
Monotone is bigger, right?
Monotone is bigger, yes. No, I mean, just compute them by hand. All right. So, are there any questions regarding those combinatorial definitions? Какие-то вопросы есть? Потому что мы сказали. Давайте вот здесь не будем путаться. Здесь действительно момент, место, где легко запутаться, можно использовать какое-нибудь не то определение чисел Гуровица, и у вас ничего не совпадет с тем, что это логические рекурсии, собственно, как и было в исходной формулировке домашнего задания. Чтобы совпало, но по суть одна и та же. Суть одна и та же. То есть понятно, что там, если вы здесь напишите, там, допустим, 1 на m факториал в определении или нет, это получится разные числа. Но смысл у них один и тот же, просто они отличаются простым комбинаторным множеством. Поэтому вам просто всегда нужно смотреть на то, как конкретно задано определение, вот, и после этого проверять, что можно сказать. Да? Определение по-разному можно брать.
Мы же потом научимся понимать, что именно считает топологическая рекурсия.
В каком смысле, что именно считает?
Что нужно там на факториалы делить или нет? Как исходных данных это понимать?
Значит, мы потом, ну вот сейчас мы это проверим просто численно на семинаре. На семинаре мы увидим численно, что они действительно совпадут вот в таком определении, то, что дает топологический рекурс. На 0,1 мы уже увидели, но там этот эффект не играет роли. Точнее, 1 на m факториал, да, вообще не играет. Нет, 1 на m факториал играет. 1 на m факториал мы уже увидели, что он играет, он там был нужен для 0,1, то, что мы обсуждали в прошлый раз. А когда мы 0,3 обсудим, мы увидим, что вот эта вот вещь, умножение на автоматизм нужно, ну, чтобы совпало все. А потом мы с вами докажем, мы действительно увидим, как это работает. В общем случае мы докажем, почему происходит такое совпадение между топологической рекурсией и числом Гуровица, но для этого нам придется немножко развить теорию. Непосредственно сразу это не видно. Там есть более сложные способы, как это доказывать через уравнение Хантинг-Джоя, но мы, наверное, подробно разбирать не будем, а сразу перейдем к другому способу, который проще. Нам придется рассмотреть вот эти вот самые, то, что называется тау-функции КП. Если кто слушал мини-курс, который Коля читал, то там про это рассказывалось, значит, мы введем понятие тау-функции типа геометрического типа КП, и там будет видно, как, с одной стороны, они связаны с числами Гуровица, это мы непосредственно увидим и разберем, и с другой стороны, они связаны с логической рекурсией, и вот через это мы докажем соответствие, и будет задача. Соответственно, вопрос. Еще вопросы какие-то? Okay, so now let's talk a little bit more about the geometric definition. Do you remember that apart from the combinatorial approach, we had this geometric approach? So we said that the Hurwitz number was, so we said that we consider the Riemann surfaces of genus G. And we wanted to count coverings of the Riemann sphere. So we have the Riemann sphere, and we have coverings, ramified coverings by genus G surface of this Riemann sphere. And we said that there is a natural equivalence on those ramified coverings. And let's maybe give an example of precisely a thing like this. So for instance, you consider a map from CP1 to CP1 where Z maps to Z squared. Okay? How does this look?
Will be a ramified covering with 2 points. Each one corresponds to translation.
Yes. So this you can see that every point, if you consider CP1 minus 0 and infinity, yes, then in this set, every point has exactly 2 pre-images. Okay, right? So, but 0 and infinity, they have just 1 pre-image. Here, 0 maps to 0, and infinity maps to infinity, and that's it. So they are the branch points. And we have 2, and they are in fact degree 2 branching points, or what we call simple branch points, right? So this is an example of such a ramified curve. Is it clear to everyone how this works? Do we have to discuss this in more detail, this specific example?
No, no, то есть
Exactly the same as what's happening at 0. So you can, at infinity, you can just introduce coordinate t equals to 1 over z. And you can see that there, this map is precisely the same in this coordinate t. Yes?
So, but except of 0 and infinity, you have just solve quadratic equation, like, yes, and its quadratic equation has two zeros, so this is 2 pre-images.
So basically, you take your sphere, then you have it from North Pole to the South Pole, and then you drag, so you wrap it 2 times upon South, okay? But at the poles, you have just single pre-image. Is clear in this example? So this is a specific example of such a map. But then we consider all possible. We can take, instead of just here is a sphere to sphere, but we can take genus G surface over sphere. We consider all possible ramified covers like that, and natural equivalence. Natural equivalence is that. I mean, there is. I mean, it was fine. Natural equivalence is that you have a homomorphism between 2 upstairs here, between your G surfaces, such that the diagram commutes. Yes? And we said that our Fourier number, H, G, mu, was the sum of one of number of automorphisms of F overall coverings F such that covering set from some set overall equivalence classes.
Ну, то есть, да, сумму по всем классам эквивалентности 1 делить на группу автоморфизмов накрытия.
Such that we said that we have P1 and so on, PM downstairs in CP1. So So we have m points here. So here we have infinity, this is P1, infinity, P1, and so on, Pm, some m points, where again m is related to g as 2g minus 2 plus m plus size of mu. And we wanted here, we required that the profile over infinity is mu1 mu n, and over pi's it's simple. The pi's are points of simple ramification, and there are no other ramifications such that over pi's ramification is simple.
Ну, это определение мы уже вроде бы давали в прошлый раз.
We had this definition.
Да.
Previous lectures. And
хотелось повторить, что такое автоморфизмы и как это связано, да.
Do we need to divide it by some factorials as mentioned previous definition?
Yes, we will need to do this in order to manage the previous definition. So we will see this. So some factor. So here we have some combinatorial factor C, which we will determine. All right, so you do remember this, yes? So we consider this sum overall 1 over number of automorphisms such that the requirements are as follows, like on this picture, like shown on this picture. So do you recall the definition, and are there any questions? Now let's see how this corresponds to what we have there in the combinatorial picture.
So let me maybe say a few words about automorphism of F because of, so what is the automorphism of the coverings, of the covering? Yes, it is, or you are going to say about it? Or...
Oh, you can say.
Yeah, so, okay. What is automorphism of covering? It is just, you may think about it as it acts. I forgot the English word. So it acts fiber-wise on the covering, and so the automorphism of F, it just renumerate the mu I forgot.
You mean the sheet of the covering?
Yeah, the sheet, renumerate the sheets of the covering inside each fiber, and so yes, it you may think about it as it is. In formally, the automorphism of the covering is just so it's like a homeomorphism of the above surface of the covering surface, such that its composition with the covering just equals to the covering itself. Yeah, so it's therefore it's clear that it means that it acts fiber-wise, and then in each fiber re-enumerate the sheets of the covering. Yes.
Let's look at our example, which we have here. Z to Z squared. What are automorphisms of this covering? Yes, it is clear that if you consider, so an automorphism is some map upstairs here, right? Some map here, let's say A.
Yes.
It's a homomorphism of the sphere here, of A, such that if you take the composition of A with your covering F, so this is F, it remains the same. So, and if A of Z is minus Z, sorry, A of Z is minus Z. So this is clearly a homomorphism of a real sphere, of your real sphere, right? Z maps to minus Z. Okay? And if we'll take the composition, if we consider F of A of Z, what will be? What will be? Z squared, which is precisely the same as F of Z. So indeed, this is an automorphism. So the requirement on the automorphism is precisely this, that it's some map from our surface upstairs, in this case CP1, but in general it's our genus G Riemann surface, some homomorphism of it onto itself, such that this composition is the same. So the same as the original thing. F of A of Z should be equal to F of Z. Okay? And how many automorphisms do we have in this case? Just two. We have the identical and this one. Why don't we have any more of them? Why can't we have some other automorphism such that this still?
Every point has two pre-images, so
Yes.
we can leave or slope, and by continuity.
Yeah, by continuity, you get a lot of those two things. Is it clear? Is it clear to everyone why we have precisely in this example, why we have precisely two automorphisms? Out of all possible homomorphisms of the sphere upstairs here, of homomorphisms A, only two of them are indeed automorphisms of this covering, namely A of Z equals to minus Z and A of Z equals to Z. Just the identical one and this one. And that's it. Is it clear? I mean, this requirement says that this requirement precisely says, let's look at it. Let's study this in general. Let's study this in general. So, we're below. Let's look at some point. At some point, P downstairs in CP1. So this is CP1. And here we have the pre-images. So these points, we consider this set F inverse of P in our sigma. Sigma is the genus G surface. So we have this F from sigma to CP1. And here are the pre-images. Our requirement that, and we have our automorphism A from sigma to sigma, right? And we have the requirement that A F of A of Z, if Z is a point in sigma, should be equal to F of Z. Okay? This was our requirement that it is indeed an automorphism. This means that what can happen? What can this automorphism do? Can it move? Well, let's look at how it acts on this point. Can it move this point to some point here on our sigma? Here we have this sheet. It goes somewhere. They can intersect. So can our automorphism A move this point somewhere here? Can it? Why? Why not?
Which one?
I mean, I look at some point in the pre-image of P.
Image is big.
Yes, I mean, by this requirement, its image should be P. And there are only, in this case, 4 points which maps to P on sigma by F. So the only thing which this A can do is just either mapping it to itself, this point, or mapping it to some of those points. Yes? And for all other points, the same thing. But this should also be a homomorphism. So it cannot take, like for instance, it cannot at the point P map this point into itself, but at some very close point, it cannot map it here, right? Because it should be continuous. It's a homomorphism. But this doesn't rule out non-trivial automorphisms completely, because as we can see here, there can be non-trivial automorphisms. As in this example, so Z maps to minus Z is fine. It is an automorphism. Okay, so is it clear now what are these guys? What are the automorphisms?
Is it true that if we take a general point and we know the action on the images of this point, then if there is automorphism, then it's...
So you mean you asked that? Suppose can we do it like that? Take a general point. There are n factorial, or not n, but size of mu factorial. Let's call it d for simplicity. So d will be is size of mu. Is the number of sheets. Okay. So over general point. Number of images over general point. So you were asking the following question. Let's take the general point. There are d factorial ways to reshuffle these d images, right? And you're asking whether we can take any one of those and uniquely extend it to the whole thing, right?
I think that not anyone, but is it unique? Ну, like this. Ну, мне кажется, что нет. Мне кажется, что всегда может продолжить, но возможно однозначно.
Yes, so the point is that it's not always possible to extend this, because it might happen that let's see some other example. So it might happen that you have let's say points P1 and P2, not P1 and P2, but for instance, we have our infinity, for instance, and here, let's say we have mu1 equals to 3, and here we have mu2 equals to 2, sorry. Or it's like this. And let's look at what happens in the vicinity here. At some point here, right? So what happens is that if you take a nearby point to infinity here, some nearby point, and look at the pre-image here, in this case you have 5 pre-images, but will you be able to like map this guy to say this guy? Why?
Because by continuity, the pre-image that has 2 levels of covering will be mapped 3 branches.
Oh yeah, you can. Here you see that if you look at those two guys and you consider what happens at this point tends to infinity. These two pre-images, they will coincide at this limit, right? And these 3 guys, they will coincide at this limit. But if you if you wanted your automorphism to map one of these to one of the others, then you'll have a problem with continuity once you go to this limiting point. Is it clear? Why there will be a problem? Okay. So now let's see how this corresponds to our combinatorial problem, which we had before. So like it was explained on the, at this point it's more or less clear who are the automorphisms and how to count their number of automorphisms, right? So now let's consider what is the relation which it was given on either on the previous lecture or on the one before that. So what was the relation to our combinatorial problem? So the relation was, let me recall it. So the relation was as follows. You said the following thing. So here you have your sigma of G of G, right? And here you have your CP1, and we have our infinity. We have points P1 and so on, Pm, right? And we take some other point. I don't remember how it was called on the previous lecture, but let's call it, I don't know, Q. Some general point Q, which is not a ramification point. Okay. Then we consider in this order. So we consider small. Let me draw it down in red. So we consider loops going around all PIs and then going around over infinity. Okay. Then over our point Q, how did our cover look? In a small neighborhood of Q, let me erase this picture and draw it only locally. So over, so what happens here over Q? Over Q, we have just it's unramified, right? So we have D sheets, okay? D sheets, and let's number them. So here we have. Let's introduce some ordering on those sheets, in whatever way. So let's say that here over Q we had some points. Let's call them A1, A2, and so on, AD. So we have D points over Q, and we introduce an ordering on them in some arbitrary way. Okay? So then when we move along this loop here, we can consider what happens with all the points upstairs. So each of those guys, it starts moving somewhere, right? And let's see what happens once we go along all the loops. So suppose we first we go around P1, then we go around P2 and so on Pn, and then we go around infinity. What happens once we return back to our point Q?
Permutation will be identical.
Yes, precisely. So once we go along, once we follow along all those loops, each of those points, it will return to itself, precisely. Why is this the case? Because you can see that these contours, which I have here in red, it's in fact the same as this contour in orange. The same in the sense that they contain all of the ramification points. And this orange contour, you can going on the back of the sphere, so you can deform it such that it's actually this small loop going back to Q, just very small loop from here. So is it clear? If we take this orange contour and deform it through this the side of the sphere which is there at the back, we can transform it to something very small contour Q going immediately back to this point Q. Is it clear? Is it clear what I said? This means that, and because if we go here, you can obviously see that for a very small contour, they never can leave their sheet. These points, if they go along very small contour, which where there are no ramification points there, so they can go back only to their sheet. Okay? Or they remain on their sheet, which means that these points, if you go along the orange contour or the red one, because that's the same, they always return to themselves. And this corresponds to a permutation on those d numbers. So, like going along a closed loop here corresponds to some permutation of those guys. And if you go along a loop which contains all the ramification points or none of them, which is the same on the sphere, it's a trivial permutation. But if you consider just one single loop out of those red guys, this can be, or in fact it will be, a non-trivial permutation. Why will it be a non-trivial permutation? Because we need to go back to this example. We need to go back to our example here, this one. And let's see what happens upstairs. So let me draw it. So here is our CP1, it's 0. And we consider some point, let's say 1. And we go along, we go like this. Whatever. For instance, like this. So this is CP1 downstairs, CP1 downstairs. And what does it correspond to upstairs? What does it correspond to upstairs? Upstairs, so here we have now the CP1, so we had our map F of z equals to b squared. What does it correspond to? And here, in fact, we have two sheets, right? So what happens? Let's see. Downstairs, once we go around 0. What happens upstairs?
upload.
Upstairs, this goes to, this is 1, this is -1, right? And, but -1, so you can, no. But -1 goes to 1, right? And these two guys are precisely our points of the pre-image. In the pre-image of the point 1, you have 2 points, -1 and 1. And once you go along this loop, they get interchanged. As you can see here, it's a transposition on this collection of numbered sheets. Yes, this is clear. This. And this will precisely the same thing will happen whenever you go along a point of simpler modification. Because locally the point is that here, when we have a simpler modification, then this means that locally you can always introduce a local coordinate near this point, such that this map near this point looks precisely like that, like f of z is z squared plus some constant. So locally, it's always like in that example, which we have there, right? So this means that, going back here, so once you go along a simple, along this loop, which contains some of the points pi, simple modification points, this means that this will correspond to precisely this thing. This will, if I consider this, maybe let's use some other color. No. So if I go along this loop, yellow one, along which goes around my simple modification point P1. So this will correspond over here. It will correspond to all of the points. I need more of them probably. So all of the points, apart from 2 of them, they will go back to themselves. So for instance, let's say that this will go back to itself. This one again will go back to itself, and then going around some one point. But this guy, it will come here, and vice versa. So is my picture clear? So if you go along this yellow loop downstairs, out of those points AI, all but 2 of them will return to themselves, but two of them will get interchanged. So this will be a transposition on this set of points AI. And the same is true about all the other PIs. So we will have some number of transpositions, and in fact, if you go along sequentially, if you go along all those contours around PIs, your transpositions will get multiplied, right? So you get a product of transpositions, and if you multiply it with, so here, infinity is not a simple ramification point, but of some arbitrary ramification, right? Specified by mu i's. So you get some permutation. So precisely, you get this condition. So here you get some permutation tau 1, tau m, and here you get some permutation, let's call it sigma inverse. This will be convenient to call it inverse for our purposes there, and you get the following condition that tau 1 times tau m times sigma inverse is equal to identity. Because as I said, if we go along all the loops, in total this is the same as going along the orange loop, and this is identical permutation. And then you can just multiply both sides by sigma. You get tau 1 and so on, tau m equals to sigma. Okay? Now we need to establish, I think we're out of time.
Yeah.
But we wanted to establish that if we count up to, if we look at all those coverings and count them with this weight 1 over the number of automorphisms, then this will be the same as counting all sets of transposition, all collections of transpositions divided by a factorial, right? Such that the cyclic type is prescribed. What does this dividing by n factorial correspond to? Dividing by n factorial corresponds to the fact that you, I mean, we introduce some arbitrary ordering on our sheets, right? And there are here over the infinity, you have also some. Sorry. You have also those sheets intersecting, like mu1, mu2, and so on, mu-n, right? But
So about what factorial are you?
No, I mean we want to see that this.
I'm sorry. There is a mistake. Again, mistake in the definition. So there are no n factorial. There are modulo mu factorial. Should be in the definition yeah, like.
So this n or size of mu?
Yeah, of course, yeah.
Are you sure?
Yes.
Yes, of course, yes. Sorry, yes. Yes. Sorry, so here it's not n factorial, but in fact it's size of mu factorial.
Yeah.
Yes.
And so, okay, to finalize, yeah, maybe yes, this modulo mu factorial is numeration of sheets of the covering, and this m factorial is the numeration of
No, but this m factorial, it should not in fact correspond. I mean, the geometric picture, you need to add this manually, this 1 over m factorial. Because
yes. Okay. We moved it from the definition from yeah.
n это количество великих, а модуль mu это сумма.
Да, module of mu is equal to the sum of all mu, so it's a degree of the covering. It's a degree of the covering.
The geometric picture size of mu is the degree of the covering, and n is the number of reimages of infinity. Number of reimages of infinity, of the point infinity. So this 1 over size of mu factorial, it corresponds to the number of ways with which you can number your
corresponds to the degree of monomial with which it goes series.
Sorry?
Модуль μ это степень мономал, который мы там рисуем.
Yes. Yes. So as you can see here, why do we get this 1 over, in this case it will be d. So size of mu is d. So by in the geometric picture, your number of exchanging the and how the different orders on those sheets, they matter. They actually do not matter. I mean, in our definition, we did not introduce this orderings, right? So we only just said that we count all equivalence classes with the weight 1 over orthomorphism. But in the combinatorial picture, we have in order to pass to the combinatorial picture, we have to number them somehow. But there are d factorial ways to do this, which corresponds to dividing over the d factorial, which is size of mu factorial, in the combinatorial question. But then, if there are some automorphisms of your covering, then they will actually correspond to the same answer on the combinatorial side. And that's why you have this 1 over the number of automorphisms on the geometric side. Let's think about this. Let's have our break until class 3.